Perfect, thanks for having us. Welcome to the Modernized Condition Monitoring with Next Generation Sensors and IoT Platforms webinar, featuring Avnet and TE connectivity. My name is Keaton Anderson, and I'm one of the speakers for today's event. I'm a Senior Customer Solutions Manager with Avnet, and my focus is on ensuring our customers have the smoothest experience on IoT Connect. Devin Brock is a Field Applications Engineer for Sensors with TE connectivity, and he will walk you through the TE Sensors portfolio and some of the hardware on today's demo. Finally, you'll hear from my colleague Stephen Detloff, who is an IoT Solutions Manager with Avnet. Stephen is going to walk us through the Quick Start demo and showcase just how quickly you can get these sensors connected to the cloud. Without further ado, I'm going to pass it to Devin to talk about TE connectivity and our HVAC use case. Devin, over to you.
For more than 80 years, TE engineers and product specialists have partnered with customers to produce highly engineered connectivity and sensing solutions that make a complicated world possible. Our focus on reliability, durability, and sustainability exemplifies our commitment to progress. The unmatched range of our product portfolio enables companies large and small to turn ideas into technology that can transform how the world works and lives tomorrow. TE is one of the world's largest sensor companies, and our products are used in a variety of industries, including automotive, industrial, aerospace and defense, medical solutions, and consumer applications. Today, we're going to be talking about TE sensors for IoT-enabled condition monitoring applications. While condition monitoring has been around for years, it is evolving with the Internet of Things, or IoT. This growth of IoT and its advancing ecosystem, which supports continuous monitoring of all factory assets, has affected condition monitoring practices and has contributed to evolving predictive maintenance or operations. Sensors are now being manufactured to include the requirements demanded by this IoT ecosystem. The latest sensor developments are being influenced by IoT trends such as miniaturization, digitization, sensor fusion, low power, and wireless technologies, while being packaged for harsh environments. As a result, sensors are progressing to enable continuous condition monitoring by collecting data, which facilitates intelligent decisions via manufacturing, learning, or artificial intelligence. Vibration, pressure, position, speed, fluid property, temperature, and humidity sensors all play a critical role within industrial condition monitoring applications. These industrial sensors help reduce downtime by predicting machine failures, increasing productivity, lowering maintenance costs, and improving worker safety. TE Sensors has a broad range of sensor technologies for IoT and condition monitoring applications, including both wired and wireless sensors. The main technologies include vibration and pressure, but also include temperature and humidity and others. Some of the key applications for condition monitoring are listed here and include everything from pump and compressor monitoring to building management applications. There are a wide range of building management and HVAC applications that require low or ultra-low pressure sensors to accurately monitor and control airflow in a building. Typical static pressure for commercial duct systems is around half an inch of water, or 0.02 psi, or 125 Pascal. Even lower pressures will be seen when looking at differential pressures, which is key in several of these applications. The first major air-moving application for these types of pressure sensors is for airflow measurements, either volume or mass flow. It's important to understand the overall system pressure. Slight positive pressure will help keep hot air outside from penetrating into the building during the summer. Negative pressure during the winter will allow outside air into the building to maintain humidity. Control of the air pressure inside the building is key to maintaining and keeping the building comfortable. The next major application is for air filter monitoring. While the algorithms are rather complex, monitoring the differential pressure across a filter can help determine when the filter is dirty, clogged, or damaged. Ensuring clean, efficient filters in a building can save a great deal of time and money, and can also help ensure occupant comfort and safety from contaminants. The next major application is variable air volume, or VAV, systems. The temperature of the supply air is held constant and the room temperature is controlled by varying the volume of air delivered. These systems are more efficient than constant volume, variable temperature systems. The last major application is for leak detection in air moving systems. Here, the sensor is monitoring the overall system pressure, and a drop in that pressure can indicate either a leak somewhere in the system or trouble with fans or blowers used to move the air, or the dampers or controls used to regulate the airflow. Now we will spend some time talking about some of the wired sensors that TE designs and manufactures, and specifically those that are used on a collaborative demo between Avnet, Microchip, TE, and Microsoft. Here is a picture of the demo, which has been dubbed the IoT HVAC airflow demo, and it was built around the use case for utilizing low-pressure board mount pressure sensors in a building management airflow application. The demo includes 5 different sensors on a Micro-E click development board, along with a Microchip W532 IoT board and a Micro-E shuttle click system to connect the sensors to the W532 board. The hardware platform for this demo starts with the Microchip W532 IoT development board at the heart of the system. It features Microchip's Azure certified module that contains the PIC32MZW1 series Wi-Fi system on a chip, which is a 200 MHz high-performance MCU with industry-leading Wi-Fi connectivity and rich peripheral options. The system on a chip not only provides a robust and secure Wi-Fi connection, but also serves as a powerful MCU core handling the entire IoT system. The module also features the Trust and Go platform, which is a pre-provisioned secure element for securely connecting to cloud platforms like Microsoft Azure. The development board also features a microbus socket, which is used for connecting CLICS add-on sensor boards manufactured by Microelectronica, a maker of hardware and software tools for developing embedded systems. Microelectronica offers hundreds of clipboards that are compatible with a microbus socket specification. Next is the Microelectronica shuttle click bundle. Since there is only one microbus socket on this board, this accessory kit is used to expand the single socket into multiple sockets, each connected by a separate ribbon cable. The expansion kit allows up to 4 clipboard sensors to be connected to the W532 IoT board. 2 shuttle clicks are used for this demo to accommodate the 5 different sensor clipboards. 5 clipboards are used in this demo, all featuring sensors manufactured by TE Connectivity. The first sensor is the ultra-low press click, which uses the SM8436 low differential pressure sensor. The second sensor board is the variable air volume press click, which incorporates the LMI S025B ultra-low differential pressure sensor. The third sensor board is the temp-hum14 click, which uses the HTU31D digital RH and temperature sensor. The fourth sensor board is the PHT click, which incorporates the MS8607, which is a combination pressure, humidity, and temperature sensor all built into one. The fifth and final sensor board is the Altitude 2 click, which uses the MS5607 high-resolution barometric pressure sensor. 2 of the sensors on the system that we did want to take a few minutes to highlight are the LMIS025B on the VAV press click and the HTU31D on the temp-and-hum14 click. The LMIS025B is a differential pressure sensor designed to sense very low pressures with high accuracy. It is based on a thermal flow measurement of gas through a microflow channel integrated within the sensor chip. The innovative LMI technology features superior sensitivity, especially for ultra-low pressures ranging from 0 to 25 pascals. The extremely low gas flow through the sensor ensures high humidity to dust contamination, resistance to humidity, as well as allowing for long tubing compared to other flow-based pressure sensors. The LMIS025B is suitable for pressure measurements in variable air volume building ventilation systems, as well as respiratory applications in medical systems. The HTU31D is a highly accurate digital relative humidity sensor with temperature output from TE connectivity. With power consumption down to 3.78 microwatts and an accuracy of plus or minus 2% relative humidity and plus or minus 0.2 degrees C temperature accuracy, the sensor provides fast response time, precision measurement, low hysteresis, and sustained performance even when exposed to extreme temperatures up to 125 degrees C in high humidity environments. The sensor is suitable for relative humidity and temperature measuring applications, including applications in building management, medical applications, weather stations, monitoring systems, and more. Using both off-the-shelf hardware and software, this IoT-enabled HVAC sensor device provides the critical building blocks for a smart, connected, and secure IoT design. The low-pressure sensing testing platform consists of a single rigid PVC tube with a computer fan on one end, which pulls air through the tube in one direction. A vacuum cleaner filter is then inserted into the middle of the tube, creating two separate chambers. Flexible vinyl tubing is used to insert the clipboard sensor in between the two chambers. The low-pressure sensor periodically measures the difference in pressure between the two chambers. Changing the fan speed results in a new differential pressure reading. Changes in the environment can easily be tracked by the other sensors, including changes in humidity, temperature, and barometric pressure. Now I will turn it over to Keaton at Avnet to discuss their IoT Connect platform that enables OEMs to easily build and deploy secure, innovative apps featuring comprehensive analytics.
All right, perfect. Thanks, Devin. So I'm going to talk to you a little bit about IoT Connect, but before I do, let's dive into who Avnet is. So Avnet is a global technology distributor and solutions provider. We've been in business for over 100 years, and we have locations and employees worldwide. And I think if you typically tend to think of Avnet, the way that you would see us is probably for our supply chain and logistics. And that's true. That's still our bread and butter. We do that very well. But one of the things that we're most proud of is that of recent, we've made some investments that we feel like has given us some unmatched capabilities. So with companies like SoftWeb Solutions and Witekio, instead of just having our traditional supply chain and logistics, we now also have things like an embedded software design group. And this enables us to do things like design firmware or application software. It really helps us to be able to close the gap on maybe some things that we had not had in the past. And so with that, let's talk a little bit about what made us kind of go in that direction. So when we look at IoT and we talk about the challenge that a customer might face when they're doing development, one of the things is that there's a lot of different aspects that go into a design. And so going from left to right, you'll see here that the first thing you're going to have to work on is hardware and firmware. So that's being able to get those devices connected. But then you're going to have to connect them into the cloud. And then from there, you're going to be able to connect them into backend systems and experiences that help you to be able to drive business decisions. And so the whole of this essentially is that IoT requires skills across multiple engineerings and disciplines. And if you don't have those capabilities, you either have to hire and spin up a team associated with that group, or essentially you have to try to bring in a third party to help maximize that and get that design created. And so what we have done is we've designed IoT Connect. And what IoT Connect is supposed to do is help close the gap across all of these different disciplines that are required and really create a single place that people can be able to go from multiple disciplines and kind of build an IoT solution. So what does this look like? So IoT Connect takes things like a connected HVAC system inside of a smart building or an industrial gateway. And its entire goal is to be able to extract meaningful business insights. So for example, in that connected HVAC system in the smart building, let's say you have different filters on different floors. You want to be able to monitor those across the building and then be able to make insights to send out maybe a maintenance crew to address a filter that seems like it might be clogged. And you don't want to have to send them to every single duct every single day to check them. It'd be nice to be able to have an interface to be able to check and send maintenance as is needed. And very similarly with that industrial gateway, if you're in, say, a manufacturing plant, you want to be able to make sure that the plant doesn't go lying down. And so you want to look at those machines, maybe something's getting overheated, and you could again be able to address that maintenance ahead of time. And so what the whole idea is try to get from those things to those insights as fast as possible. And the way that IoT Connect is actually going to do this is it's going to use a single pane of glass web experience to help you do things like manage your devices, view and analyze device data, secure data and devices. And it's going to build that on top of a layer of cloud provider microservices. And this could be either with Microsoft Azure or AWS. We have both versions. So for example, with AWS, this would be things like IoT Core or Greengrass. On the Microsoft Azure side, this would be things like IoT Hub, Cosmos DB, device provisioning service. You have a couple of different examples there. And so really the whole goal of what we're trying to do is as quickly as possible get you from the things that you need to have information about and help you start extracting business insights and taking actions from that. Okay, so let's take a look at IoT Connect from a smart building use case example. So if we take that hardware that we discussed earlier and we connect it into the cloud, we're going to get something like this within IoT Connect. So we have a front-end interface that we can be able to interact with. And this enables us to be able to do things like set up entities, which is our way of being able to do segmentation by devices and locations. So you could imagine you could have hundreds of different endpoints across multiple buildings in different cities, all set up within IoT Connect and managed from one experience. Additionally, we can support multiple different device types. So we talked about how TE connectivity has a wide portfolio of both wired and wireless sensors. IoT Connect can connect to all of them. We have an easy way to be able to get connected with many different device types. And then last but not least, we have the ability to do things like smart rules. So if we go back to that example that Devin talked about earlier, where if the filter gets clogged, it's potentially problematic, we could be able to set a rule that says if it goes over a certain pressure amount, then trigger an email that we could send to our maintenance crew to let them go look at that particular filter. And so IoT Connect gives you a ton of different ways to be able to get connected with devices and manage them all from a single pane of glass experience. And so with that, I'm going to hand over to Stephen Detloff, who's going to talk about this example in more detail and walk through our quick start experience. Stephen?
Thank you, Keaton. Hi, my name is Stephen Detloff, and I'm an IoT Solutions Manager with Avnet. And today I'm going to be taking you through a quick start guide in order to connect TE sensors to the Avnet IoT Connect platform where we can visualize that data. The first thing we'll want to do is open the URL that's displayed on the screen here and navigate to the quickstart.md file. And I'll make sure this URL is available in the collateral along with this webinar and as a follow-up once this webinar is posted. As we jump in, I'm going to just quickly transition to the first section, which is the introduction. As you can see here in the introductory section, we're going to be walking through the instructions on how to quickly connect the microchip WFI32-IoT development board to Avnet's IoT Connect platform. We're going to be leveraging this microchip development board as a gateway. Essentially, it's going to provide the Wi-Fi backhaul we need to take the telemetry from the TE sensors and move that to the IoT Connect platform. So the TE sensors we'll be going through today are all mounted on micro-E clickboards. These clickboards have a universal header that can connect to this WFI32-IoT board. I'll go ahead and show you what that looks like here. So you can see, here's a picture of the board. Here's the click header, and all of the TE sensors will be mounted on boards that can easily plug into this header on this board here. Some of the key features of the microchip board are it has a built-in hardware secure element, which we'll be leveraging today to have secure device to cloud connectivity. We'll be looking at the temperature and light sensor telemetry also provided by that board. We'll demonstrate some device to cloud commands as well using the onboard switches. And although not required, we can further visualize some of the telemetry by using the clickboards. And in fact, we will be going through that portion today, more than just one. The firmware we provide along with this guide supports a variety of clickboards. I'll be going through and connecting 4 of them today, all in parallel, but you can follow the links here if you're interested in purchasing some additional clickboards for yourself. With that being said, I'm going to navigate down here to the hardware setup section to talk about the environment that I have set up here and help you get yours set up along with me. So I do have a note in this section that while the Micro E clipboards aren't necessarily required to follow this guide, doing so does give it a lot more visualization, and we really want to show and highlight the TE sensors and some of their capabilities. So do recommend picking up a few of those from those links I just showed above. I'm actually connecting multiple up to 4 at a time by also leveraging what's called the shuttle click adapter. So I'm going to go ahead and open this link here. This allows you, as you can see, plug one device into the microchip development board, and it breaks out 4 different ribbon cables such that you can connect 4 different click adapters simultaneously. That's how I have my environment set up here today, and that's what I'll be following through with as I go through the rest of this guide. So I'll close both these windows and move on. What you'll want to do is, once you have your clicks available, you'll want to make sure you connect them to either the development board directly or to that shuttle click adapter, ensuring that you're lining up the ground pins to the ground headers, and they're labeled via a silk screen on the board, so just make sure you pay attention to that. Once you have your clipboards attached, you'll want to make sure you can connect that to your PC using a micro USB cable. Once you do that, Windows should automatically detect and install the mass storage USB drivers required to make that board accessible. You'll know that it works if you open up your My PC. You should see a new removable device labeled WFI32-IoT, and that will contain some configuration information we'll go in and adjust momentarily. But for the time being, make sure you have that device shows up, and then we can move to the next section about programming the firmware. The first step here in programming the firmware is to download and install the Microchip MPLAB X IDE package. Specifically, you'll want to get version 6.05. I know this is not the latest version, however the newer versions have not been tested, so I cannot guarantee compatibility. But go ahead and open up this link here. This is for their MPLAB ecosystem download page, and you can scroll down and search the archives for version 6.05. I believe you are able to run multiple versions in parallel, so if you do have a new version already, don't worry, you can still install 6.05 with no problems. So you want to download that and go ahead and install that package. Make sure that you tick the box for 32-bit device support and MPLAB IPE. These are the only 2 packages that you really need to worry about during the installation if you're concerned about space on your PC. Once that's downloaded and installed, the next step will be to download the firmware binary package. Again, this is a pre-compiled hex file that we've already created that has all the support for the TE sensors we'll be going through today. So you can go ahead and hit right-click and save this to a location of your choice. I personally tend to want to save these files to the root of my computer, so C:, I have a folder called TE where I've saved, you can see the zip file here, and I went ahead and already extracted the .hex file out of that zip archive there. So go ahead and do that as well. Once you have that unzipped, you can hit your start menu and you can type in or search for IPE, and go ahead and launch that application. That is the MPLAB IPE, or their programming tool from Microchip. Once you launch that application, as you can see it's loading here on my computer, you may be prompted, if it's the first time connecting your hardware, to flash a new update, and you can see I have one here, so I can click here to make my application up to date. I'll go ahead and hit next, accept the terms, and hit update. All right, if you've already connected, you may not have an update available. In that case, don't worry, you can just continue on. What you'll want to do though is make sure that your settings in this tool match what is outlined in the guide here. So for the device entry box, you'll want to make sure it says WFI32E01. And then for the tool, you want to make sure it starts with Curiosity/Starter Kit PKOB4. If you verified both these are correct, you can go ahead and hit connect. And while that is connecting, again, you may be prompted for some certain updates, but you'll know you're connected when you have the option for a disconnect here. So you can see It grabs some information from the board regarding the toolpack version and whatnot, and we're ready to go and continue to move forward. To program this device, we first need to tell it where to locate the hex file we wish to program, and you'll see there's a field labeled hex file here, and over to the right there's a browse button. So I'm going to hit the browse button here, and I'm going to navigate to, you can see C:/TE. This is where I extracted that .hex file. Please make sure you're not selecting the hex file still within a zip file. It needs to be fully extracted. So go ahead and grab that hex file and hit open. And it will tell you that the hex file has loaded successfully. Once you see this, you're ready to go ahead and hit the program button. You'll see that we get some information here about programming beginning. It's going to calculate some memory ranges and move on. So I'm going to let that kind of program here in the background and just kind of scroll down here and show you what you can expect to see. So once the programming of the board finishes, and it only takes about 20 seconds, we should see a blue programming complete, and then it's going to hold and reset. So the board will be held and reset there, waiting for us to take some action. So I'll flip back over to my programming tool, and sure enough, my programming is now complete and it is being held and reset, which is great because this means our firmware is now programmed and we can move on to the next stage of configuration, which is going to be creating an IoT Connect account and getting that all set up. So if you don't already have an IoT Connect account, this is the step where we'll go ahead and create a trial account. With this trial account, there's no credit card required, but you do get access to all the features of the platform just for a limited time basis. The IoT Connect platform is compatible with both AWS and Azure hyperscale clouds. I've written this guide to leverage the Azure underlying hyperscale cloud, and I suggest when you create your trial, you can just use the same as me and make sure you select the Azure version, just so everything else will match up as we continue on. One note, be sure to check your spam folder. Oftentimes the temporary password sometimes will end in that folder. If you'd like additional information on the IoT Connect platform, subscriptions, and what are the limitations, you can follow this link here to get some more information on that trial. But assuming you have your account already or you've just created one, the next step we'll move to is creating the device template in step number 5. So in this section, we'll be importing what's called a IoT Connect device template into the platform. And a device template is defining the type of telemetry in a JSON format that the IoT Connect platform can expect to receive from an edge device. We're defining one here for the WFI32, and it's going to contain all the type of telemetry we can expect to receive from all the sensors that I listed out before up in the introductory section. Device templates can be made from scratch, but for the sake of today, I went ahead and pre-made a device template and made it available for you here. So you must right-click on this, hit Save Link As, and then I recommend just placing it in the same folder with your hex file or wherever you're saving your other TE collateral. Once you've downloaded that, we're going to go ahead and import that into IoT Connect. So if you're not already logged in, make sure you log into your IoT Connect platform. You should get a screen very similar to what you see here once you're logged in. You'll be presented with a dashboard with some subscription information here as well. But what we're going to want to do is first create a device template. And the way you do that is go over to the little MCU CPU looking icon here, which is called Devices, and we're going to click on Device. This section has all the information and all the different tools that are associated with edge devices in the cloud. So you can see we have templates, devices, commands, rules, firmware, history, and some data export. But we have no devices and we have no templates. So let's start off by creating or importing a device template. So I'll click on Templates, and then I'll click Create Template. And again, we can create one from scratch by inputting all this information here. I'm going to go ahead and hit Import, and then I'm going to go browse to that file that I have in my C:, and it's called device_template.json, hit OK, and hit Save. And once I do that, you'll notice that I have attributes that I've imported. There's a whole bunch of attributes here. We've got some device commands for controlling some LEDs, which we'll get to later in this guide. But assuming all this looks good, I'm all set. I've imported my template. I can click back to my template list, and now you'll see that we have a template created for the WFI32 IoT development board. I will flip back over to the guide here and show that we've completed now this section 5. And I will mention that if you'd like to learn more about templates and how to create them from scratch, you can follow this link here to our IoT Connect documentation repository and dive a little deeper into that. Now that we have a template set up, we'll want to create a specific device for that template, and that's done here in section 6. In this section, we'll be creating a device to associate with the template we created in the previous section. You can have one or more devices all associated with a single device template. As a reminder, the device template is really just defining the type of data the platform should expect. So if I had 5 microchip devices all sending telemetry from TE sensors, they could all be associated with one template. There is a short walkthrough here on how to create a new device, but I'll go through and show you manually how to do this in the platform. So switching over to the IoT Connect platform, you can see we're still in our template screen, but if I go back down to the bottom, I can select devices. And right now we'll see there's no devices currently created in this account, so I'll go ahead and hit create device. The first thing I'll want to do is select the device template. And again, I'm creating a device and I want to associate it with this template because this is the type of data that I plan to send to the cloud. And you'll notice some of the fields change here. Under entity, we'll want to select Avnet. If you created a trial account, you'll likely only have one object in here. It's likely going to be Avnet. You can just click that entity. For the display name, we can go up here and you can see I already have it pre-populated, but I'm going to call it Stevens WFI32 IoT device. And for the unique ID, what I'm going to do is actually grab the serial number from the device. To do that, what I can do is go back to this PC icon in Windows Explorer and open up the removable drive that was created. You'll see a variety of files in here, and what I'm going to do is pick the device.pem, which contains my device certificate, which we'll just use in a moment here, and I'm going to copy this first serial number here because this is unique to my device, and go ahead and Control-C for copy, and I'm going to paste that here in the unique ID. So now it's telling the platform that it should be expecting a device with this specific unique ID to be connecting. The next step is the device certificate. So again, like I mentioned at the very beginning of this guide, we're going to be using the hardware secure element. And in this case, we're going to be using the self-signed certificate built onto the device. So you'll probably want to do something different in production, but for the sake of demonstrating the security features, I'm going to leverage the certificate on the device. So I will use my certificate, have that button checked, and under the device certificate browse field, I will click the link to browse. I'll go to my device, and I'm going to click the device.pem file. Make sure it's not the root or the signer, it's the actual device certificate, and hit open. And then the next step is I will hit save and view. This is going to create the device, and you'll see that it's currently in a disconnected state because we're going to have to do a reset on it, and we can do that in just a moment. And we'll have some different fields we can look at here after we reset the device. So I'm going to tab back over here to the guide, and you'll see these are the steps we've already completed. We navigated to the mass storage device, we grabbed that device information from the .pem file, and we completed entering the entity, the device certificate, and we clicked save and view. So the next step will be to configure the device to tell it how to connect to the platform. And we'll do that here in section 7. So now that we have the device template created in the IoT Connect platform, along with a unique device associated with the serial number of my specific board, now we'll turn to the device itself and do some final configuration to allow it to connect to my Wi-Fi network and to allow it to authenticate with the IoT Connect platform. The first thing we'll do is configure the Wi-Fi credentials. There's 4 different types of networks that are supported for connecting with this device. We can use an unsecured network, a WFI protected access 2 or WPA2, WEP or WPA3. Most common routers today use WPA2. and that's what I'll be using today for this demo. So what you'll want to do is navigate back to your removable drive. And again, if this isn't showing up in your computer, you may need to do a restart or just unplug and replug it in if you haven't rebooted it after initial programming. So make sure you do that. We'll go ahead and open up this drive, and we'll see that there is a file called wifi.cfg or Wi-Fi config. And we're going to program this in the format here where it is, you can copy this, and then you're going to want to replace my SSID with the network name and my password with your password, and then leave the number 2, which specifies it's for the Wi-Fi protected access 2. So I will pull up my file here, and you can see here is my network name, and then the password for that, and then the 2. So once you've done that, you'll want to save this file, and you can open this in any text editor. It's just a text file, and just make sure you don't change the file extension. You'll want to save that and close that file. And then the next thing we'll want to do is configure the IoT Connect account. So in the IoT Connect account, we're going to require to put 2 different pieces of information in there. One is called the CPID, and one is called the ENV. You can see in these instructions here, if the contents do not have any text in there, you'll want to restart this by just ejecting the drive, reconnecting the board to your computer, and then those files will automatically be populated. But assuming you have that cloud.cfg file in there with these 2 fields in there, we can continue on. So similarly to the Wi-Fi file, there is a cloud CFG file. I'm going to go ahead and open that right here. And you'll notice we have to fill in 2 pieces of information. We're going to need the CPID and this environment. And this is going to tell the device how to connect and which instance of the IoT Connect account to connect to. Both these pieces of information can be obtained from within the IoT Connect GUI. So if I flip back over to this IoT Connect GUI here, and then if I scroll down to Company Profile or Key Vault, I'll go to Key Vault, probably the easiest. You can see my CPID or my company ID was associated with my specific account. So I'm going to go ahead and click the little copy button next to this, and then I can go back to my notepad and paste that value in there. Similarly, I can look at my environment. Again, if you're doing a trial, it's most likely just prod. You can copy that and you can paste that into the environment variable here too. Then you'll want to hit save on this file. Ensure that that saves to your USB removable drive. And once that's done, you can go ahead and just close those files. That's all it really takes to publish, to configure the board. We've published both the CPID and environment. Now the board knows how to interact. We've already completed the configuration on the cloud side. So now it's time to go ahead and fully reboot the board. And then we can start to do some visualization. So we saved it. You can either hit the RST button or reset button on the board. I personally just like to completely remove the USB cord and let that reboot. So I'm going to go ahead and do that now. And while that's rebooting, I'll move down here to the visualization section, which is section 8. We can use the dynamic dashboard feature of IoT Connect to visualize the data we're receiving from the TE sensors. These dashboards can be created from scratch on a blank canvas, or they can be created and exported and saved as a template for others to use. I've created a couple different dashboards that are available here in the bullet pointed list, but for today, we'll take a closer look at the TE sensor-centric dashboard. You can right-click and save link as, and we'll be saving another JSON file. This provides information on the layout of the dashboard, so you'll want to save this in the same location you've been saving your other TE files, and it's called TE_sensor_dashboard. You can see I already have mine here, so I'm just going to go ahead and hit cancel. Before we go ahead and create the dashboard, which I'll do in just a moment, let's verify we're actually receiving that information and our device is connected. So by heading back over to the IoT Connect GUI here, we can click on the devices icon and then the device submenu. And we'll just want to verify that our device status over here says connected in green. And then if I click on the device unique ID and then latest value, I can see that there are some values for some of these different sensors that are flowing in here. So with that checked off, let's go ahead and click on Create Dashboard. And up here, we have an option to create a new dashboard or a new device dashboard. And that's if we're going to want to create one from scratch. But since I've already created one for us to use today, let's just go ahead and click on the Import Dashboard. And then we'll have a file browse path here. We'll want to go select that JSON file we just downloaded a moment ago. So we'll hit Browse. We'll click TE Sensors Dashboard and hit Open. And now we need to tell that dashboard where to get the data to populate. And to do that, we'll say, hey, we want to use the template we created a moment ago, WFI32IoT, and we'll want to select the device that is unique to you. So this is my serial number, so I'll pick that device there. And then we'll give the dashboard a unique name like TE Sensors Dashboard. There's some other options here. You can just leave these at default for today and go ahead and hit Save. This will take that information, create the dashboard layout, and put us in the dashboard edit view. Within the dashboard edit view, you're free to move around, grab these widgets and organize it however you'd like to lay out the dashboard. You can use the fields at the bottom here to add different widgets and associate them with different pieces of telemetry. But because this is already laid out the way I'd like to, I'll just go ahead and hit Save in the top right to commit this dashboard layout. So once I hit Save, we'll see that there'll be some initial data that's starting to populate in here. We have some line graphs that are displaying some pressure, some atmospheric pressure, humidity, temperature, and you can see that it's grabbing this temperature from a variety of different sources. I have personally 4 clicks currently connected using the shuttle click device. I have the altitude, the variable air volume, the pressure, humidity, temp, and the temp and humidity. And those pieces of information are being displayed on the screen here. We can see the altitude as reported in meters. We have the MCU temperature that's being reported by the actual microchip board here. There's some firmware version information and some light, which is reading a lux value from the actual board itself. As I scroll down here, we have a button counter, which will grab any time that I press the button on the microchip board. We'll have a device command menu here, which I'll come back to in just a moment. And there's some links to signing up for IoT Connect, a link to the quick start guide here, a link to buy some additional TE sensor products, and to the TE connectivity homepage. So with that, I'm going to flip back to the guide so we can finish off this section and move into the next section about sending commands, which is section 9. In this last section, we'll show how we can send commands both from the device to the cloud and from the cloud back down to the device. We can do that by leveraging the 3 LEDs that are built onto the board, and by using some commands, we can turn them on and off from the cloud. And then additionally, we can leverage the user-definable buttons on the microchip board to indicate when they've been pressed and display that on the dashboard. So let's head back over to the IoT Connect window. If I scroll down to the bottom here, we can see there is a button counter here. And I'll go ahead and bring up my webcam that I have fixed on my board here. You'll see there's a little blue light, and across from that we have 2 user-definable buttons right here. So if I reach over and press these buttons, I'll press one a handful of times and one once or twice. You can see that it's counting those up here in the bottom left corner. We're getting 4 different commands being sent and 1 on this button here. I want to make this window smaller here, and we're going to take a closer look at the device commands from the cloud. So here I have the LED controls. So you'll notice I have a blue LED and a red LED on. So if I can go to LED blue, I pass it a command parameter of off, hit execute. You can see that blue LED is now turned off. I can go do the same thing with that red LED. I'll go ahead and tell that command of off. And our yellow light is just our data in action, our data moving light, sending telemetry. And I can go ahead and turn the green LED on here. And you can see the green LED has come on here. So just being able to demonstrate that 2-way commands, there's a variety of different use cases where that can be useful. So I'm going to head back over to the guide here, and now we've wrapped up section 9. So as a quick recap, we've connected the microchip WFI32 IoT board to IoT Connect to use as a gateway for taking the sensor telemetry data from the TE connectivity sensors mounted on the shuttle clicks and move that to the IoT Connect platform. We've used the dynamic dashboard capabilities to visualize that data, and we've also demonstrated how we can do device commands both from the edge to the cloud and from the cloud back to the edge. These have all been done using the wired TE sensors. TE also has a wireless portfolio of sensors that can communicate via LoRa. While outside the scope of today's webinar, we do have additional resources that you can find along with this webinar to talk about how we can connect and enable those LoRa sensors via Avnet's IoT Connect platform. So keep an eye out for those in the collateral attached. And now I'm going to hand it back to Devin, who's going to quickly talk about some of the TE wireless sensor options.
On the wireless sensing side, this slide highlights some of the technological trends driving innovative wireless sensor products from TE Sensor. These include developments such as integrating multiple sensing technologies, advanced signal processing, and integrated diagnostics. These trends enable simplified installation, real-time analytics, increased accuracy, and much more. TE manufactures wireless sensors with a range of technologies including vibration, pressure, temperature, humidity, and others, and includes features like edge computing, embedded processing, as well as self-diagnostic capabilities. TE has developed a platform of wireless sensing products, all based on a common platform, including body style, processing electronics, a high-density industrial battery, and more. Current supported technologies include vibration, pressure, humidity, and temperature. Supported wireless communication protocols include both BLE and LoRa, with HAZLOC certified products available. The IP66, IP67 package rating allows use in harsh and unfriendly environments. The new TE8 series of wireless vibration sensors combines a piezoelectric accelerometer, frequency data analysis, and multiple wireless data transmission options combined into one compact battery-operated device that measures both vibration and temperature data. It was designed for harsh environments and is certified to work in hazardous locations. Some of the key characteristics and features of TE's wireless vibration sensors include options for either BLE or LoRa communication protocols, features a piezoelectric high-frequency sensing element that allows for early detection of machine failures. High-frequency vibration analysis allows for significantly earlier detection of potential problems, as opposed to low-frequency analysis. Also, bearing wear and other localized faults related to friction, impact, or surface defects often generate high frequencies in their early stages, and these can be captured. Also provides full edge analytics, including fast Fourier transforms and peak detect. Includes an operating lifetime of at least 10 years with up to 10 years of battery life. Some of the key applications for TE's wireless vibration sensors include oil and gas equipment, internal combustion engine power plants, motors, pumps, compressors, and autonomous guided vehicles, or AGVs. On the pressure side, the new TE6 series of high-precision wireless pressure transducers eliminates the need for hard wiring, providing remote process control and monitoring through seamless digital communication. Our products are certified for intrinsically safe hazardous locations. They meet all applicable requirements for radio frequency communications and are CE and RoHS compliant. These high-accuracy sensors are enclosed in a stainless steel and polymer housing. Wireless pressure transducers are suitable for liquid, gas, contaminated, and mildly corrosive fluid measurements. The port design uses no internal O-rings or organics exposed to the pressure media, which provides excellent durability and long-term performance. Some of the key characteristics and features of TE's wireless pressure sensors include options for either BLE or LoRa communication protocols, battery powered with long life capability, onboard data analysis with programmable actions, intrinsically safe hazardous location certification, pressure ranges from 29 psi to 5,000 psi with digital 24-bit ADD conversion, as low as 1% plus or minus 1% total air band, and excellent long-term stability, as well as wide operating temperature ranges. Some of the key applications for TE's wireless pressure sensors include oil well and pipeline monitoring, corrosive fluids and gas measurement systems, industrial process control and monitoring, refrigeration systems, pumps and compressors, hydraulic and pneumatic systems, smart logistics, agriculture equipment, and energy generation and management. TE's wireless humidity sensors will be available in early 2025 and provide both humidity and temperature sensing in a single package. Like the rest of the wireless sensing portfolio, there are options for both BLE and LoRa communication, as well as intrinsically safe certification, long battery life, and much more. Applications include corrosion under insulation for oil and gas, chemical, and industrial pipeline systems, moisture and oil applications, as well as for environmental and agricultural applications. TE's wireless temperature sensors will also be available in early 2025 and provide reliable temperature sensing in a rugged and reliable package. Like the rest of the wireless sensing portfolio, there are options for both BLE and LoRa communication, as well as intrinsically safe certification, long battery life, and much more. These sensors are built using a patented dual-layer sensor head design that allows for accurate temperature sensing at high temperatures up to 260 degrees C, while isolating the sensor head and electronics from the high temperatures. Applications include corrosion under insulation for oil and gas pipeline systems, steam traps, transformers, power generators, pumps, and HVAC applications.
So I'm going to jump back in here. We just want to say thank you so much for attending and for paying attention during this webinar. We hope you learned something. We're going to move to the Q&A section now, and so I'm going to hand it over to our moderator.